Hi, everyone. Okay, so VSEPR, VSEPR, it stands for valence shell electron pair repulsion. Basically, this entire part of the unit is focusing on the electrons, the fact that electrons are negative, therefore they repel each other, and based on how many things, and when I say things, you guys remember from covalent structures, we have lone pairs and bonds that can appear on a central atom. So depending on how many lone pairs and bonds total that the central atom has, we get different shapes. So today, that's what we're going to talk about. We're going to talk about the shapes that are made by atom combinations when they make molecules, based on how far the electrons are pushing it apart. They're trying to maximize their space, so how far they can go apart determines their shape. So I'm going to go through like the basic ones, and then we'll look at a table that has all of the possible variations. Okay, so again, electrons are negative, therefore they repel each other, and they want to be as far apart as possible. They want to maximize that distance that they are apart. So for the first example, for a 3-atom molecule, SN stands for steric number. It's kind of an old term. Your book does use steric number, I believe. So if you are reading your book and you see that, all it means is electron pair geometry. That's what this EPG here means, electron pair geometry. They really kind of mean the same thing. It's how many electrons are on the central atom. So if you look at this one, we have beryllium as the central atom, and it's making 2 bonds. And that's it. There's no lone pairs on this central atom. Beryllium is in group 2 on the periodic table, so it has 2 bonding electrons, which it means it's going to make 2 bonds. Here it's making bonds with fluorine. So those electrons, to get as far apart as possible, are going to be on opposite sides of the beryllium, which give it a 180-degree angle. It's a straight line, 180-degree angle, and we call that linear. That one's pretty easy to remember. It's very straightforward because it's linear. It's a line. The other ones do get more complicated, but each of the names do sort of represent what it looks like. The next one, if I have a 4-molecule atom, so that means, or 4-atom molecule, so that means a central atom and then 3 atoms surrounding it. There's many ways we could have this. So again, steric number 3, it's again just how many things are on our central atom. So looking at our example over here, we have carbon with 2 hydrogens and then an oxygen. So if you were counting how many, again, things, lone pairs and bonds that are on our central atom, carbon is our central atom. It's surrounded by the hydrogen and the oxygen. And you would say I have 1 bond here, another bond here, and a 3rd bond here. Even though there's 2 bonds because it's sharing 4 electrons, it is 1 double bond. So we have 3 electron pairs sort of on that central atom. We have a single bond, and a double bond. So that's 3 total. And the furthest that these electrons can get away from each other to maximize the distance gives us a 120-degree angle between each of these. This one is actually also in the plane. So if I wanted to go, like if there was another one over here, it would be 180 degrees. Like they're all still in the same plane. So we do call that trigonal planar. That's the farthest we can get apart when we have 3. If I were to bend one down, these angles would get smaller. Because right now, like the angle between like this right here is sort of like 180 degrees. I know that's hard to visualize, and hopefully, I'm not sure if you're watching this before or after we did the lab, but hopefully in the lab that'll make a little more sense. You'll be able to see these like 3D structures. That'll help a little bit. But these are in the same plane, and there's 3 things coming off the central atom, so we call that trigonal planar. Trigonal means 3, and then planar, they're all in the same plane. Steric number 4, again, that just means 4 things coming off of the central atom. Here with our methane example, we can see it has 1, 2, 3, 4 bonds, 4 single bonds. We call that tetrahedral, so the electron pair geometry is tetrahedral. And you can see sort of in this picture here with the pyramid, we have 1 going up and then 3 going down. And notice these 3 are not in the same plane. Here they were in the same plane, but these 3, they're not, specifically because this one on top is sort of pushing all of these down a little bit. So the distance between each of these when there are 4 bonds is 109.5 degrees. So those are pretty much like the 3 main ones. Anything after that is sort of like, well, if you took off a bond and you replaced it with a lone pair, we give that a different name because it technically makes the bonds a little different. So tetrahedral is a good one to look at that with. If I were to take off this hydrogen and put a lone pair here, that lone pair takes up a little more space than the bond does, mostly because the bond is sharing the electrons, whereas the lone pair is not. So because those lone pairs, like the electrons, you can think of as sort of staying in that place, they take up a little more space, which makes these no longer 109. It makes them like 107. And then again, if you put 2 lone pairs, it'd make it like 104. So it continually sort of goes down the more lone pairs you put on there. So that's what we're going to look at. Whoops, I went the wrong direction. Wait. Oh, no, I didn't. Here we go. So that's what we're going to look at here, lone pairs. So they are, again, more repulsive than bonded pairs, again, because the 2 electrons are not being shared. Here they're being shared, which means they have to take time to go around the hydrogen and then around the nitrogen and then around the hydrogen and then around the nitrogen, so forth, whereas these kind of just stay on the nitrogen. If you take like a snapshot. So that means that lone pairs take up a little more. So if I have something that is, again, steric number 4, that means its electron pair geometry is tetrahedral, no matter what. If I ask you for the electron pair geometry, and there are 4 things on the central atom, so here's 1 bond, 2 bond, 3 bonds, and a lone pair. That's 4 total. That is going to be tetrahedral electron pair geometry. Now, if I ask you for the shape, then I'm just asking you for basically what does it look like? And so the shape for 3 bonds and 1 lone pair is trigonal pyramidal. So you can kind of see it makes a pyramid here, but without that bond on top, it's not really like pushed up. It's these sort of all become like in the same plane with 1 going up. That's what we call trigonal pyramidal. It sort of makes a pyramid. And then instead of having a bond up here, it's like a lone pairs on top. So these 3 other atoms sort of make a period with the nitrogen sort of being on top with that lone pair. And again, because the lone pairs push a little harder than the bonds, we get a 107.3 degree angle instead of the 109.5 that you saw on the original tetrahedral with 4 bonds. So again, here I have 4 things in the water example. I have 4 things coming off of the central atom. I have 2 lone pairs in this case and 2 bonds. So that's 4 total. It still has an electron pair geometry of tetrahedral, but now its shape, because I have the 2 lone pairs, its shape is bent. So its shape, if you are looking at an atom, the shape is really based off of the bonds. The lone pairs matter because they're making the bonds into a specific shape, but the bond is the shape that we're talking about. So electron pair geometry for water is tetrahedral, but the shape is bent. And that's what we see here is we have this bent shape with the oxygen as sort of the point in our bent, and then the 2 hydrogens coming off. Again, it still has a tetrahedral electron pair geometry, but it has a bent shape. We also call that molecular geometry. Let's see what else. Oh, angles. So again, tetrahedral was 109.5. Trigonal pyramidal, this example says 107.3. Honestly, if you Google it, you're going to see like 107.5. You might just see 107. It's okay as long as you know that it's getting less by about 2 degrees, 3 degrees, that's okay. So again, when you add another lone pair, we go from the 107.3 to 104.4. Again, with this example, if you Google it, you're going to commonly see 104.5. Again, that is okay as long as you know, again, it's going down. Every time you add in a lone pair, the bond angle is going to get smaller and smaller because the lone pairs push harder on the shape than the bonded pairs do. Okay, so here's sort of, you guys have this chart in your book. It's on page 190. However, it's smaller than this. It's a little more limited. I like this one because it does go into the expanded octet. So where it says 5 right here for number of bonds and then 0 lone pairs, everything below this is an expanded octet. So that means the octet rule doesn't apply. It won't have 8 electrons in the central atom. It's going to have more. Everything above this the octet rule does apply. So you can see here 2 bonds and 0 lone pairs was our linear shape. That was the very first one that you guys saw. 3 bonds, 0 lone pairs, that's trigonal planar, which again is the second example I did. And then I didn't actually do an example of this where you have 2 bonds and 1 lone pair. We again it still have the electron pair geometry as trigonal planar, but now the shape would be bent. Tetrahedral we did go over. We said 4 and 0, that's tetrahedral. And notice all 3 of these are tetrahedral electron pair geometry, but their shapes are different based on how many lone pairs they had. So that was this was the last slide that we went over, but just kind of put in a table form. So I think it helps to see it like this. Again, the one in your book is a little more condensed than this because it doesn't go as detailed into the expanded octet ones. But I do think it's good to have this in your repertoire. All right. So if you have any questions, please let me know. But that's it. Thank you.